In most of the application of physics, we need cylindrical coordinate to describe the motion of an object. In cylindrical coordinate, you have three axes x, y, z. This is your x axis, this is your y axis, and this is your z axis. And you have a coordinate. Suppose you have a point P and you have three coordinates. One is rho, phi, and z. This rho is your radial distance and phi is your azimuthal angle, or you may say the angular variation, and this is your z coordinate, and z coordinate is your, we generally say, meridianal or meridian. This is the change in the meridian. So when you calculate the velocity or the acceleration in cylindrical coordinate, all these three coordinates will change. That is, radial distance will change, the azimuthal angle will change, and the meridianal also change. This is a three-dimensional variation of the cylindrical coordinate, or the velocity or acceleration you can find out in this type of variation. You see, this is a cylinder in which the radius of the cylinder is changing. That means the radial distance is changing. Okay, and this is your angular distance. You see this red plate. When this red plate is rotating, it is making some angle with this z axis. Okay, actually the angle phi is the angle in xy plane, the angle in xy plane, because when r will change, that is, sorry, when the rho will change, then what will happen, there will be change in the azimuthal angle in the xy plane. And this is your, you see this white plane, now it is green. This plane is along the change in the z direction. This is the change in the z direction. So you have variation of three coordinates, one along rho, that is along the radial distance. You see, when the cylinder is expanding, your rho is changing, and when this angle is changing, that is phi is changing, then also there will be variation of phi. And when the movement will be along the z, then also you have velocity along z axis or acceleration along z axis. And this type of variation we generally encounter when water flow in a straight pipe. In straight pipe, there will be no change in this diameter of the pipe. If there will be change in the diameter of the pipe when water flows, then you can say there will be change in the three coordinates. Similarly, when heat distribution in a metal cylinder, if you take the heat distribution in a metal cylinder, then also you need these coordinates, that is your cylindrical coordinate. And also when you find out the position of star in galaxy, you also need the cylindrical coordinate, but only if you there will be change in radial and azimuthal, then it is called polar coordinates. And in case of cylindrical coordinate, you see the rotation is counterclockwise. You see the rotation, it is in counterclockwise, and there will be change in positive height. There will be change in positive z, or change in height along positive z. There will be no change in the negative z axis. Now let us find out how you calculate the velocity in cylindrical coordinates. The position vector in cylindrical coordinate, suppose, is given by the vector rho, that is equal to I cap x plus j cap y plus k cap z, and we know x is equal to rho cos phi. If you draw a perpendicular here, then this will be rho cos phi, and this value will be rho, y value will be rho sin phi. So if you put x equal to rho cos phi and y equal to rho sin phi, then rho will be equal to I cap rho cos phi plus j cap rho sin phi plus k cap z. Suppose this is equation number 1, but the unit vector in cylindrical coordinate we have discussed in detail in the previous video about the unit vector. So unit vector in cylindrical coordinate, we write it either rho cap or e rho cap, that is equal to I cap cos phi plus j cap sin phi. So in place of I cap cos phi plus j cap sin phi, here if you take common rho, then this will be equal to this unit vector e rho cap into rho plus k cap z. So this will be the value of rho vector, that is the position vector, and if you take the derivative of this position vector with respect to time, then you can calculate the velocity. When you calculate the derivative, you have two components, you have two factors, rho and e rho cap. So e rho cap derivative of rho, then rho derivative of e rho cap into a plus k cap derivative of z with respect to t. But if you calculate the derivative of e rho cap with respect to t, this is the unit vector e rho cap. You watched the previous video how e rho cap is equal to this much, and if you calculate the derivative of e rho cap with respect to the unit vector e rho cap with respect to t, then this will be phi dot e phi cap. So velocity vector will be equal to rho dot e rho cap plus rho phi dot e phi cap plus k cap z dot. You have to remember this velocity vector. Then how you will find out the acceleration in cylindrical coordinate? The velocity vector we have found out, and if you take the derivative of the velocity vector with respect to t, then we can find out the acceleration vector. So you find out the derivative of the velocity vector with respect to t, and here you have two derivatives of unit vectors. One is e rho cap and e phi cap, and you find out the derivative of e rho cap with respect to t, so that it will be equal to phi dot e phi cap. Similarly, derivative of e phi cap with respect to t, this will be equal to minus phi dot e rho cap. I have explained how e rho cap is equal to I cap cos phi plus j cap sin phi in the previous video. Similarly, I have also explained how e phi cap is equal to, or the unit vector along the azimuthal plane is equal to minus I cap sin phi plus j cos phi. Then you, here j cap, then you substitute the value of this and this in equation 1 here, and you calculate the expression for the acceleration. So by substituting these values of 2 and 3 in 1, we get the value of acceleration is equal to this. So you have three components. This is along radial, and this component is along the azimuthal, and this is along the meridianal. So you have three components of the acceleration, and also you have three components in case of the velocity. So you should remember these expression for velocity and acceleration in cylindrical coordinate. This is very useful in the motion of 3D helix. In case of 3D helix or 2D helix, in case of 2D helix, the rho will not change, but in case of 3D helix, the rho, that is the radial distance, will change. This is a 2D helix. Here the rho in the cylindrical coordinate, the rho will not change, but this is a 3D helix where the rho will change. phi also, here phi and here also the phi will change, the z value will also change. So in this type of expressions, there is use of your cylindrical coordinate.